Hello, we are from Biosport presenting our study for biofuel production in Javeri Valley. This presentation is intended to review the current process of manufacturing biofuels and designing new process in Javeri Valley. For the development options, we explore the alternative source of fuels, feedstocks, and separation method. Two main global interest biofuels are bioethanol and biobutanol. For feedstocks, alternative option would be soybean, corn, and beets. Next, our alternative separation methods would be pure distillation, pure vaporization, and liquid-liquid extraction.
When we review the current red flame process, we identify three key challenges for the ABE product separation. First is low yield of butanol due to toxicity to microorganisms. Secondly is high operating cost from the accumulation of ethanol in recycle streams. And lastly, bacteriophage infection leading to slower growth and declined solvent production.
Next, we look on proposed design for Javeri Valley. Batch operation is done once after the other, therefore feedstock is only added in the beginning, while continuous fermentation did not stop in between, and feedstock are added at regular interval. Therefore, batch operation is manageable since fermentation is a complex operation with multiple specifications to meet. To reduce the need for repairing and number of workers on site, the operation suitable for the Javeri Valley would be batch operation.
Advantages and disadvantages of ABE-based fuels and conventional fuels are shown in this table. With the context and needs of Funai, ABE fuels are better ethically and allow for the independence from foreign entities.
Here is our new design. We decide to operate a batch fermentation instead of a continuous one and stagger the schedule of batch fermentation, enabling us to operate distillation continuously. Firstly, the aqueous phase, which is enriching water, is feeding into a stripping column C2, and its column aims to separate a very big fraction of water as bottom product. We will also add ethylene oxide to the reactive distillation columns C1 and C3 to remove the risk of water by reacting with the water to form ethylene glycol, leaving the bottom products. As a result, removal of water by the reaction breaks the azeotropes, which helps butanol to be purified without any need for separation agents and recycled streams. As to the specifications, here is a mass fraction of 4 components at the reaction in the reactive distillation columns. This can be complex to the locals, therefore the process must be scaled down to a manageable size of about 60 times 40 meters, and our process should not be disadvantaged by a scale down as it produces a higher yield and works at a lower cost.
The main design constraint encountered is the production of ethylene glycol, which will cause extra investment in the transportation of raw material and the energy consumption for serious reactions. Nevertheless, the expense brought up by these two elements is relatively small compared to the total annual cost, so it still costs the least among all designs in the end. Brazil is the largest producer of sugarcane in the world. Although the valley is located inside the rainforest, it's not difficult to achieve molasses of sugarcane from other parts of Brazil. The separation process will be more efficient if we can minimize the amount of acetone before it is finally separated. From researching, some strains can ferment substrates into butanol and ethanol with little and even no acetone in the production. Therefore, no more separation between ethanol and acetone are needed anymore. In the continuous process, continuously adding the broth may increase the risks of contamination and mutation. Hence, batch fermentation is a simpler method than the continuous one.
The presence of azeotropes in the mixture makes the separation more difficult by increasing the equipment size and energy requirement. Thus, we decide to use reactive distillation columns to obtain high economical efficiency.
In our process, 3 components are present together in column 4. Using Aspen, we created a residual curve diagram of the 3 species at 1 atmosphere. The residual curve diagram tells us that there are no azeotropes, and we therefore do not need azeotropic distillation, and a ternary phase diagram cannot be modeled. This is a result of removing a high percentage of water in the earlier process steps, leaving us with a stream into the butanol column that is highly pure in ABE. The residual curve also tells us that the output of our butanol column will be pure in butanol, even with a small number of stages, meaning our process is highly efficient and will not cost much. Process steps that may limit the rate of butanol production are fermentation, pressure in the columns, and water stripping. Fermentation, as the composition of the ABE mixture needs to be high in butanol and low in ethanol and acetone for the number of stages to be reduced. Decreased pressure in the column results in higher yield but will reduce rate of butanol production. If enough water has been stripped, there will be higher concentrations of butanol being produced in column 4. Rate of butanol production is therefore larger, and so water stripping efficiencies directly affect the production.
Large amounts of land will be used by the plant as it has many components, and also it is required for planting the feedstock sugarcane. This can lead to deforestation, as part of the forest will be removed to provide enough land area. Deforestation will result in environmental issues such as soil erosion, increase in carbon dioxide levels in air, which is one of the greenhouse gases, and loss of biodiversity through loss of habitat for some species. Focus of agriculture will be directed towards sugarcane more than food supplies, which means land used for food will be replaced by sugarcane.
The ethical issues that need to be considered while introducing this process to the consumers in Javari Valley are health and safety, because keeping everyone involved in this process safe is very important. There should be a plan on how to mitigate and prevent all analyzed hazards. Workers' rights, because the indigenous people would have to do the manual work, so they must be treated and paid fairly. Environmental impact, the production of the biofuel should be environmentally sustainable. The process of making the biofuel is very water intensive, therefore the amount of water left for other things could reduce drastically and eventually lead to a water scarcity. If there's a reduction in the availability of water, this affects energy and food production.
Potential of groundwater contamination and effect on the possible water supply as shown here in this table. However, these effects can be mitigated through a well-engineered process with proper safety and waste management procedures put into place.
Our source of fuel is sustainable since it's miscible in water and non-polar solvents, the feedstocks are environmentally friendly and inedible, and the demand of feedstocks minimizes the greenhouse gases emission. External assistance is not necessary, since the design are mostly distillation column which red flame are spectized in, therefore any malfunction can be locally repaired by team members. Having to use external assistance from outsider can break the trust between Funai and the local tribe, as entrance for non-indigenous people is prohibited.
The process has its negative sides, however, there are ways to reduce them. For example, environmental issues can be minimized by treating waste products before disposing them. The contact with people who will introduce the process to the Amazonians can have a positive impact if only those who belong to the Funai team are allowed to communicate. Moreover, having the fuel produced at home means they will have self-sufficiency of fuel and therefore less materials will be needed to be imported and reliance on the outside world is decreased. Considering all the previous points, BioSpark strongly recommends the implementation of the process. In conclusion, the new process has its disadvantages. It requires ethanol oxide transportation and storage, initial setup expenditure, local land use and knowledge on reactions. However, our new process works to reduce the overall costs, increase the rate of bioethanol production, reduce runtime and manual labor via conversion to batch process, reduce wastage via broth recycling, and will encourage the use of local produce as fuels, forming relations between the locals and Funai.
This is our bibliography. Thank you for listening, and we hope to hear from you soon.